All right, let's jump right in. What on earth could a line of code possibly have in common with a screaming, high performance race car? I know, it sounds like two totally different universes. But it turns out there's this hidden shared language that connects them, and that's exactly what we're going to explore.
Seriously, it sounds like the beginning of a weird joke, doesn't it? I mean, on one side, you've got these super smart algorithms figuring out your next favorite show, and on the other, you've got the pure brute force physics that keeps a car glued to the track at insane speeds. But trust me on this one, if you stick with me, the answer is going to reveal something really fundamental about how we make sense of pretty much everything.
So let's picture this. On one side, you have a coder, a data scientist, buried in lines and lines of Python. And on the other, you have a mechanical engineer, surrounded by blueprints, equations, the smell of machine oil, maybe. One is playing with abstract data, the other is literally bending steel. You'd think they couldn't be more different, right? Different worlds, different tools, different goals. Or maybe not. Okay, here's the secret sauce. At their very core, both of them are doing the exact same thing. They're building models of reality. They're creating these simplified versions of incredibly complex systems. The data scientist is trying to model messy, unpredictable human behavior, and the engineer, they're modeling invisible, powerful physical forces. And that is the key. They just speak different languages to get it done. Each one has its own specialized language to describe, to predict, and ultimately to control these systems. So to really see what I'm talking about, let's get a little bit fluent in both of them. We're going to start with the language of data. All right, first stop on our tour, the massive, sometimes kind of chaotic universe of data science. This is the language people use to make sense of that endless flood of digital info that's all around us every single day. Yeah, looking at a map like this, it can feel like a lot. I get it. But here's a better way to think about it. Don't see it as just a big, scary list of tools. Think of it more like a complete dictionary and grammar guide for the language of data. It's got it all, from the tools that draw you pretty pictures to these incredibly powerful machine learning algorithms. So let's crack open that dictionary and look at some of the key vocabulary. You've got data visualization tools. Those are basically the illustrators. They turn mountains of raw numbers into stories and charts that we can actually look at and understand. Then you have programming languages like Python and R. Think of these as the verbs. They're the action words you use to actually do stuff with the data. And then there's the big one, machine learning. This is kind of like a predictive grammar. It uses these recipes or algorithms like regression, which is great for predicting a number, like a movie rating, or classification, which is all about putting things into buckets, like comedy or drama, all to find patterns we'd never see on our own. So, by speaking this language, a data scientist can build a model of you, basically, a model of your viewing habits. They can look at what you've watched and then, bam, predict with sometimes scary accuracy what you're going to want to watch next. That's the power of this whole thing. All right, so we've seen how coders model our digital world. Now, let's literally switch gears. We're going to get our hands dirty with some real-world nuts and bolts physics. Time to trade that keyboard for a wrench and a calculator. So we're going from this huge, sprawling universe of human data, and we're zooming way in to one single, super precise physical problem. How do you calculate what a car is going to do when it's pushed right to the edge in a fast turn? Okay, take a look at this. This is an anti-roll bar. And I know it looks pretty simple, right? It's just a bent piece of metal that connects the suspension. But its job is absolutely critical. It's the thing that stops the car's body from leaning over, from rolling when you take a corner hard. And to really understand how it works, an engineer has to speak its language. And in this particular language, the most important word is stiffness. It's not a vague term. It's a super precise measurement of how much that bar fights against being twisted. To figure that out, engineers use a very specific dialect. We're talking the formal language of physics and calculus. Now, don't worry, we're not going to get lost in a bunch of scary formulas. Just think of it like a three-step conversation. First, the engineer figures out the stiffness of that long main part of the bar. Step 2, they figure out the stiffness of the shorter arms on each end. And finally, step 3, they just add it all together to get the total stiffness for the whole component. See? Not so bad. And that is the result of that whole conversation. By speaking the language of physics, the engineer creates this perfect little mathematical model that describes exactly how this one part will behave. And that model, that's what keeps the car stable, safe, and glued to the road, even when it's being pushed to its absolute limit. Okay, so let's recap. We've seen two totally different worlds, right? A coder modeling what movie you like, and an engineer modeling a piece of steel.
now it's time to pull back the curtain and see the one universal language that they actually both share.
So check this out. On the left, you've got the data scientist's toolbox. On the right, the engineers. And yeah, at first glance, they look totally different. You've got Python over here and physics formulas over there. But look a little closer. See that? They're both built on the same foundation. They're both speaking math. And they even share some of the exact same dialects, like linear algebra. It's right there in both toolkits.
And this really brings us to the big idea of this whole thing. It doesn't matter if you're modeling why customers leave a service or how a car's body rolls in a turn. The fundamental process is exactly the same. You use a formal language to describe a system, predict what it's going to do, and maybe even control it. You know, when you think about it, these specialized languages, whether it's code or calculus or even chemistry, there's so much more than just stuff you learn in a textbook. They are, without a doubt, the most powerful tools humanity has ever invented for understanding our world and for shaping it.
So, next time Netflix serves up the perfect movie for you, I want you to picture that race card glued to the track in a high-speed turn. Because they both come from the exact same place, that deep human need to create languages that can explain the world. And that leaves us with a pretty cool and kind of huge question, right? If math is a language, what other new worlds are just waiting out there for us to discover, once we figure out the right words to describe them?